Allow them to get in? No, not required.
Already there. Yeah.
Already there.
Huh. Yes, yes.
You're watching YouTube. Yes.
Around 170 something you can. I think somewhere here we stop. Okay, here I will stop. Let me see that. So shall I? Okay. Okay. So, good evening, all of you. Welcome to the 8th lecture on solid state NMR technique and basic aspects of solid state NMR spectroscopy. Hope you might have already received the assignments which has been uploaded the last week or last week. So 2 problems are there. Kindly go through the problems. So both are of similar type only. One is on tin oxide, tin 119 NMR, and another is based on phosphorus 31 NMR. So I have given indication in the class. And in fact, for one composition, I have also calculated the structural units. So kindly go through that. Any doubts or any clarification, you can ask me in the next 3-4 classes. So at least by the end of this month, kindly submit the assignment. So today we are going to the lecture number 8. So last class we have done a very important technique called C30, cross polarization. The technique is known as cross polarization, CP. CP followed by mass, magic angle spinning NMR experiment. So what is CP? CP is nothing but the polarization transfer or cross polarization. Transfer the polarization from proton to carbon-13. And there is something just like that through vacuum you cannot transfer. There should be some medium to transfer. And this medium is nothing but the dipole-dipole coupling. So through dipole-dipole coupling, we are transferring the population from protons to carbon-13. We have discussed at least, I think, 25-30% of cross-polarization experiment, but I will continue it today so that it will be more clear to you. It's a very versatile technique because if you don't do that, you will not get a meaningful signal from any of the carbon compounds. So a lot of carbon compounds can be done with the help of this NMR of lot of carbon compounds can be carried out with the help of this cross-polarization magic angle spinning experiments. It is nothing but a signal enhancement technique in which we means very less abundant nuclei like carbon-13, nitrogen-15, silicon-29, etc. Their signal can get enhanced by this technique. So it is essential that dipole-dipole coupling is important for this. Without dipole-dipole coupling, this transfer will not take place. So dipole-dipole coupling one has to maintain. Then only we will get a cross-polarization. So this pulse sequence we have discussed, because here in this pulse sequence we have two nuclei are in resonance. One is proton and another is carbon-13. So this is an example of a double resonance technique, double resonance. Normal NMR like phosphorus 31 NMR or proton NMR or silicon-29 NMR, etc. single pulse, means it's a single resonance. Whereas here double resonance, 2 nucleus are undergoing double resonance. So that is why once they undergo resonance, then they communicate each other and then population get transferred. That is why it is called a double resonance technique. So what are the steps involved? This also I have indicated you. The first step is use a 90-degree pulse. Probably this 90-degree pulse, 180-degree pulse, all those things might have discussed in your previous classes. The moment you apply a 90-degree pulse along the x-axis, that is why we call it the pi/2x, the magnetization of protons. This we are applying to proton nucleus, and the magnetization of proton, something. Sorry. So the moment you apply a 90-degree pulse along the x-axis, what happened? Because of this the applied magnetic field is along the z-axis, and you are applying a force along the y-axis, x-axis. So then what happened? The resultant will be along the y-axis because it's a cross product. And once you have cross product, the direction will be mutually perpendicular to the 2 axes. So the magnetization comes on the y-axis. because H0, which is nothing but the applied magnetic field is along Z axis and the pulse is applied along the X axis, the resultant will be in the mutually perpendicular to the X and Y axis, X and Z axis, that is why it comes to the Y axis. Now, the moment the magnetization comes on the Y axis, you lock the magnetization. How you can lock the magnetization? By applying a pulse again. You change the radio frequency in such a way that the magnetization get locked along the Y axis. That is what we are doing it here. Let me see. See, we are immediately after the immediately the phase of the radio frequency shifted to Y axis by turning 90 degree and continue to irradiate. That is why we see continue to irradiate. You can see from here. We continue to irradiate in the Y axis. So the whatever magnetization which has come on the Y axis, they remain there because there is a locking or there is a irradiation of magnetic field which is going on in the Y axis. So we flipped the magnetization from the X axis to the Y axis, and we are retaining the magnetization in the Y axis with the help of a radio frequency pulse which is applied along the Y axis. That is what we call it as the magnetization locked along the Y axis. See the locked magnetization you can see here. Whatever red color is nothing but the locked magnetization. It was in the X axis, it was Z axis of the applied magnetic field. We applied the field in the X axis initially, the magnetization come to Y axis, and then we locked the magnetization in the Y axis by applying a radio frequency field and changing it to the 90 degree. Means it has come to the Y axis itself. So what is the radio frequency field? That radio frequency, let us say as B1H, where B1 is nothing but the second field. Second, why first is nothing but the applied magnetic field, that is B0. It is indicated as, or it is given a notation B0 because it's a static field. And this B1 field is applied to lock the magnetization along the Y axis. That is called the local field. Correct, na? So now the local field which you are applied is B1 and that is along the Y axis. So the magnetization is locked along the Y axis, and this process we call it as a spin lock. We have locked the magnet. We are not allowing magnetization to decay because we are applying a magnetic field, and the magnetic field is along the Y axis, and hence the whatever the magnetization of the nuclei, which is also concentrated or the aligned along the Y axis. So this is the second step. First step I applied told it is a 90 degree pulse. The second step is nothing but the shifting of the RF field to Y axis so that spin locking take place. And the third step is what happened. We do one thing, we irradiate the S spin. So there are two spins are there as I mentioned in the pulse. One is I spin, which is nothing but proton, and another is nothing but the S spin, which is nothing but the carbon-13. Only this I and S are only for notation and distinguish from proton and the carbon-13. Because proton we are giving I spin as indication as I, and the carbon-13 we giving indication as S. So here the interaction between I and S, I spin which is proton and the S spin which is carbon-13 is the subject matter of discussion. So their interaction we are studying, their transition, their population transfer we are studying in these slides, or I am describing it through these slides. So first thing I have applied 90 degree pulse, then I have locked the spin, second step. So now the I spin is along the Y axis, that much is clear to you. Now what I am doing, now I am going to apply another RF radio frequency. See, already one radio frequency is there. Now second radio frequency, which is called indicated as H1S. First what I applied is H1I, that is for I nucleus. Now another H1 I am applying, another magnetic radio frequency with a field strength H1 and indicated as H1S. And then it also comes to what, then now this also can come to the Y axis. That is what it is indicated here. That also comes along the Y axis. It remains in the Y axis. So we have brought the proton magnetization or the I magnetization on the Y axis. Similarly, we have also made the carbon-13 magnetization also on the Y axis. That is what I am writing it here. See, the I magnetization is along the Y axis, and the S magnetization, which is nothing but the carbon-13, that is also along the Y axis. So two magnetizations are in the identical axis. Correct? Now, both are in the Y axis and point in the same direction. Now, if you do one thing in such a way, you adjust the H1 and the H1I and the H1S, because these are variables which we can adjust. By adjusting H1 and the H1I and the H1S, if you can make this condition, that is nothing but omega product of gamma I and the H1I is equal to product of gamma S and H1S. What is gamma? Gamma is zero magnetic ratio. That is a constant that cannot be changed. Gamma of proton is same. We cannot change it. Similarly, gamma of S nucleus, which is nothing but C13 for the time being, is also same. So gamma I and gamma S we cannot change because they are universal constant. They are evaluated by nuclear physics experiments, and that we cannot change. That's a constant. These are called zero magnetic ratio. So what we can change? We can change the H1Y and H1 for I, means the radio frequency field strength corresponding to I nucleus, and we can change the radio frequency field strength corresponding to the S nucleus. Change in such a way that this product become equal. Okay. That's the,
Can I
yeah, please.
interrupt you?
Yeah.
Since you are applying this to magnetic field
Yes.
on the y-axis.
Yes.
Why each nuclei is not experienced the sum of that?
Huh. Yes. In a fluid we have yes variety of nuclei, but each have different frequencies.
Frequency is different, but applied field is H1I and H1S.
Yes.
So total field is now H1I plus H1S.
Yes.
Right?
Yes. Yes.
So I spin is not experiencing this total sum of the field.
Because that it will feel some field will be experiencing. Yes, will be experiencing total sum of H1 plus HS.
Right.
There will be, yes. That is, but these are in gases compared to the applied field which is in 10⁴ gas. These values will be a small number. But as you are told, it will be expressing the sum of these values. Some of these values will be explained in addition to the dipolar coupling interaction.
Okay.
So some will be there. So you have to adjust such a way, H1 and H1 in such a way that the product of these two, you can increase H1 or you can decrease H1. First, you cannot increase H1 much because already gamma E is very high compared to gamma S. So by adjusting H1 and H2 in such a way that the frequencies of product of these two can be made equal. You are right, no doubt it seems a sum. But the relative concentration can be changed in such a way, but because the gamma I nucleus will feel more of H1.
Right.
Whereas gamma S will feel more of HIS. Whereas gamma I will feel more of H1I and gamma S will feel more of H1S.
Yes.
But there will be a mutual cross will be there. I mean, there will be a contribution from H1S to HI, gamma I or the I nucleus, and there's a contribution from H1I.
Physically, how these two fields are applied?
Through one coil, sir. Through there is application.
Single coil or
In solid state NMR, only one coil is there. Through single coil only the time scales will be different. Through single coil only we can apply.
okay.
Both the signals, both these pulses. Both these pulses can normally in solid state NMR only single coil is only there.
And these pulses are pulse
Yes.
signal, not the continuous.
These are in pulsed form. And also one more thing, sir, the carrier frequency for because pulse as such pulse we cannot apply. We take a pulse and mix it with the carrier frequency. So carrier modulated pulses we are applying. Carrier modulated pulses. For example, if you do in our system, for example, we have got a 400 megahertz machine. Because this 400 megahertz is for proton nucleus, 400 megahertz. For carbon 13, it comes around 100 megahertz. So the carrier frequency of proton is 400 megahertz and the carrier frequency of carbon 13 is 100 megahertz. So we take this pulse and then modulate this carrier frequency with the pulse.
Okay.
And for example, for proton irradiation, we take a 400 megahertz carrier frequency and modulate with pulse. For S nucleus, which is carbon 13, we take a 100 megahertz carrier wave and make it with this one. So the extent will be somewhat, still it will be different because carrier modulated pulses are coming. So, but still the effect will be there. One or the other will be there.
Okay,
So,
please go ahead.
Yeah. So you have to apply in such a, because gamma I and gamma S are constants. This cannot be changed. So product of these two, you have to apply in such a way that the product of these two become almost same. So this condition we call as a Hartmann-Hahn condition. So once the Hartmann-Hahn condition is reached, the frequency, Lamarck frequency or the in the rotating frame, this we call it in the rotating frame. In the rotating frame, the product of this and this one, this product of gamma S and H1S and the product of gamma I and H1I becomes same. In other words, in the rotating frame, the frequency of proton nucleus becomes same as the frequency of the carbon 13 nucleus. So once the frequency becomes same, then communication become more effective. For example, I have mentioned in the last class also, if the two bases are going on in the same speed, or same velocity or the same speed, then you can transfer some object from one bus to another or one vehicle to another if they are same speed. But if they are going in different speeds, nothing can be done. Here, the same condition is applied. The frequency of proton nucleus and the frequency of the carbon-13 nucleus were brought with the help of suitable variation in the H1 and HI, and this gives rise to the proper communication between carbon-13 and H, and this is due to population transfer. So how the population transfer occur? That also I will explain to you. See here, the Lamar frequency you may be knowing. In the basics of NMR, we say Lamar frequency is nothing but omega is equal to gamma H0. What is H0? H0 is nothing but B0. B0 is nothing but the applied magnetic field, and gamma I is a zero magnetic ratio. Similarly, gamma S is nothing but omega S is nothing but gamma S into B0. In other words, since we are always replacing B0 with H0, we can say omega I is equal to gamma I into H0, and omega S is nothing but gamma S into H1. Correct? Na? Gamma S into H1. The B1 and B0 can be replaced by H0 and the H1. So under Hartmann-Hahn condition, that what happened? We have modified the value of HI, H1I and H1S. So under Hartmann-Hahn condition, instead of writing omega, we can write with this ohm symbol, and ohm of I is nothing but gamma I into B1I, and ohm S is nothing but gamma S into B1S. Okay, this way we can write. So you see, these vectors are processing at gamma I. The I vector is processing at a frequency of omega I, not omega I, ohm I, and S vector is processing at a frequency of ohm S. So ohm I and ohm S become equal. That is why a communication become possible. So this is what vectorially I am explaining what is a Hartmann-Hahn condition, what is cross polarization. The frequency has become equal, and as a result of this, the population can be transferred between I and S nucleus. So to give you further how the population transfer when the energy or when the frequency becomes same is, you can also see by the concept of spin temperature. So sorry, there is one S is there, Curie's temperature, that I forgot. What is concept of spin temperature? Any magnetization, you can always express like this. This is nothing but Ni is the number of nuclei, gamma is nothing but, as I mentioned, ferromagnetic ratio, H is Planck's constant, I is the spin value which is half for both the proton as well as carbon-13, and H0 or B0 is the applied nucleus, and TL is nothing but the laboratory frame temperature, which is room temperature. We know laboratory frame temperature is nothing but a room temperature. This is called the equation in the lab frame. For any nucleus in the lab frame, this is the equation. Same thing you can convert to rotating frame. In the rotating frame, what we are doing, because in the rotating frame, we are assuming that the frame is rotating at a frequency of the carrier frequency, at a frequency corresponding to the H1 frequency for proton, and as a frequency corresponding to the carbon-13 frequency for carbon-13. Why? Because for carbon-13, let us say 400 megahertz NMR machine. In 400 megahertz NMR machine, the magnetic field is a constant. It is around 9.7 something Tesla. So the moment you say 400 megahertz means the proton frequency is 400 megahertz. Correct? Na? The magnetic field is fixed. That proton, if you consider number of protons is a variable, gamma I is fixed, I is fixed. I is nothing but plus half. So lattice temperature or the laboratory temperature, that is called the lab frame temperature, that is denoted as L, is room temperature. And you can calculate very well M is said, which is nothing but the magnetization of I. But the moment you go to rotating frame, we assume that the frame is rotating at the carrier frequency of the carrier frequency. Frequency of the carrier. Carrier, what is the carrier frequency? Which is nothing but 400 megahertz for proton. So if you consider that, if you rotate it in the rotating frame, what happens? This expression changes to rest everything is same, only the temperature is indicated by TR of characteristic of I. This is the rotating frame temperature. Remaining everything is same. And another thing is that the magnetic field H0 is replaced by H1. Why H1? Because in the rotating frame, we don't feel the magnetic field of the applied static magnetic field. That is very, very high. V0 value, which I am telling around 9 point something Tesla in the case of 400 megahertz. We will not see that magnetic field. Instead, we see the magnetic field created by the radio frequency, pulse modulated radio frequency. So this is important, pulse modulated radio frequency. So that is called H1, H1 of I. In fact, it will be more specific if I indicated here H1 of I. So this is the equation in rotating frame. Now, if you see, this is the lattice temperature, laboratory temperature, or laboratory frame temperature. Sometimes people say also as lattice temperature. And this is nothing but the rotating frame temperature. But under Hartmann-Hahn conditions, what happens? Frequency same, the magnetization exchange occurs, and you can always relate MRI is equal to MZI. So if you take this as equal, then you can always say the rotating temperature of I nucleus, which is nothing but the proton, is nothing but laboratory temperature into applied radio frequency field created by the applied radio frequency divided by static field. So this is a very, very important equation. The rotating frame temperature of the I nucleus or rotating frame temperature of the proton nucleus is nothing but the laboratory frame temperature of the proton nucleus multiplied by the applied radio frequency along the y-axis as well, and the static field which is already existing in the case of a NMR machine. For example, in the case of a 400 megahertz machine, this is around 9 point something Tesla. And this will be in forms of 9.04 Tesla means around 9 into 10 raised to 4 gas. Whereas here this H1 will be in terms of Q gas. And this is nothing but the laboratory frame temperature. Now if you will go further, so the same expression I have written here for the sake of continuity. So if you write here H0 as I mentioned is of a very high value, it will be in few Tesla. So 1 Tesla is nothing but 10 raised to 4 gas. Whereas H1 will be nothing but 10 gas. So if you see this value now, if you see this value, if you take the ratio, it will become 10 raised to minus 3. So what I want to confirm is that the temperature in the rotating frame is 10 raised to minus 3 times of temperature in the laboratory frame. Suppose the laboratory frame temperature is 300 Kelvin. So the rotating frame temperature will be 300 into 10 raised to minus 3 or 0.3 Kelvin. So similarly, the same expression is also valid for proton carbon-13 nucleus. This is for proton I nucleus and this is for S nucleus. S nucleus you see here, S nucleus, we have S is for S nucleus, R for the rotating frame. So the rotating frame temperature of the S nucleus can be given by this expression. Now you tell me which will have lower temperature and which will have higher temperature. Suppose you take I nucleus and suppose you take S nucleus, which will have low temperature compared to the which will have low temperature, whether I will have low temperature or whether S will have low temperature. Can you guess or can you calculate from this expression and assume that there is Hartmann-Hahn condition? For example, there is a Hartmann-Hahn condition means what happened gamma y in gamma I, which is nothing but the gamma of proton, and this is nothing but the H1 corresponding to proton, and this is nothing the gamma S of carbon-13 or gyromagnetic ratio of carbon-13, and this is nothing but the H1S of carbon-13. You see here gamma of proton is 267.52. We cannot do anything, which is a constant value. So gamma is fixed here. Whereas for that carbon-13, what happened? The free gamma value is 67, very less. So the product for this equality to take place, H1S should be larger than H1I. Is it clear to you? For this Hartmann-Hahn equality to carry or to retain, what happened? The value of H1S should be higher than the value of H1I. Because gamma E of proton is higher, we should have a lower value of H1I, then only we can have this equation possible or this equality possible. So H1S is higher than that of H1I. H1S is higher than that of H1I. So if you know that H1S is higher than that of H1I, the H0 is a constant. Applied magnetic field doesn't change. It is 9.04 Tesla means it remains as 9.04 Tesla. And the laboratory frame temperature cannot change. It is 300 Kelvin means 300 Kelvin. So invariably, what will happen? The rotating frame temperature of the S nucleus is higher than that of the rotating frame temperature of the I nucleus. Is it clear to you? Hope it is clear to you. Any doubts or any clarification, please discuss with us, we can discuss this. Please raise your hand, or you can stop me after the lecture. You can just see somebody is raising point or not. The two people are there. Okay. Any questions? Okay. Okay. Maybe towards the end, or maybe then.
At the end of the talk.
Yeah, end of that one, you don't again ask. So is this clear to you? The rotating frame temperature of carbon-13 is always higher than that of the rotating frame temperature of I nucleus, which is nothing but the proton. So you have a hot nucleus and you have a cold nucleus. Once you have a hot nucleus and once you have a cold nucleus, see, cold nucleus, what happened? You have a lot of population in the ground state. Once that if you reduce the temperature with Boltzmann equation also, you can understand that the ground state population will be higher. But if you heat it, what happens? Ground state population will decrease and the population of the excited state will increase. So the ground state population of the proton is much higher at this condition, under Hartmann-Hand condition, because of the lower spin temperature, and hence the population can be transferred from the ground state to the S nucleus, which is nothing but the carbon. In other words, another way of understanding is also like this. See, one is proton, which is cold. Proton is a cold nucleus. Why? Because its rotating frame temperature is less. Whereas carbon-13 is a hot nucleus, because H1 is higher, so its rotating frame temperature is higher. So if you take a cold body and if you mix a hot body, what happens? The hot body also become cold because it will lose heat and it will lose heat to the cold body. So the hot body become cold. So if you consider the same logic here, the S nucleus become cold. So once the S nucleus become cold, ground state population of the S nucleus increases, and this will, the moment the ground state population increases, the absorption cross section increases, and you see enhancement in the absorption cross section, or not cross section, the extent of absorption, and you see enhancement in the signal. This way, signal get enhanced in cross polarization. Hope it is clear to you. And another one minor point also I should say here. See, the hot body coming into in contact with a cold body, and as a result of this, the excited state, ground state population increases, and there is an increase in intensity takes place. That is one aspect. That is one point. Another aspect is that if you see the spin, okay, this is again same thing only. TRS, the rotating frame temperature of S nucleus, is greater than the rotating frame temperature of the I nucleus. That is why we see an enhancement. And this enhancement of the population transfer or the cross polarization will take place till what time? Till the temperature. You see here, the temperature in the rotating frame of both I and S nucleus become same. Once they become same, they stop population transfer. Another one minor point is also there, which I should say. If you see, protons relax faster compared to carbon-13. Carbon-13, the relaxation times are smaller. T1S is of the order of few minutes. For a carbon-13 nucleus to relax, it takes few minutes. Whereas for proton, within seconds, it can undergo relaxation. So what is happening is, we can excite so many times proton and transfer the population to carbon-13. So that way also, it is advantageous. So that is why these are the two parameters using which you can enhance the carbon-13 signal. So that is where you get enhancement in the carbon-13 NMR. So 2 points I want to make it here clear here in carbon-13 CP mass NMR. What is the advantage of this cross polarization? One is there is an enhancement in the intensity. To what extent the enhancement will take place? The enhancement will take place the ratio of gamma I by gamma S. If you see roughly carbon-13 and proton, gamma I, gamma S is around 4. So there is a 4 times enhancement in the signal intensity. And for nitrogen-15, gamma I by gamma S is around 10. So we have 10 times increase. So if you do a cross polarization experiment with the carbon-13 and nitrogen-15, the enhancement factor will be different, and we can have 10 times enhancement for nitrogen-15 and we have got around 4 times enhancement for carbon 13. So that last point which I have mentioned here also, just now I have mentioned the relaxation time of the proton is quite faster. So multiple times you can excite and transfer the population to carbon 13 and we can get good signal intensity from carbon 13. As polarization is derived from the protons, which is typically relaxed faster than low gamma nuclei, the recycle delay of the experiment can be typically faster. We can do number of times this transfer. So just a brief theoretical aspect also, the Hartmann-Hahn conditions, once it is matching in the dipole Hamiltonian, we will have 2 terms will come into picture. Otherwise, mostly a homonuclear coupling only will be there because J and K will be same, proton-proton interaction only will be there. But if there is a coupling, very good coupling, very good population transfer between I and S, then the flip-flop term, which I have mentioned in the second class, the B term, that also contributes to the Hamiltonian. So that is what I want to convey here. So otherwise, normally homonuclear coupling only is there. So homonuclear coupling is there because if you want heteronuclear coupling, the plus rising and lowering operators will be not an energy conserving process. So the B term also will be there when you have a Hartmann-Hahn condition and when there is a proper communication for the polarization transfer between E and S. This is just for your information. So if you don't have a Hartmann-Hahn, if there is no exchange, then mostly the coupling is between II and ES spins. Because IS spin is an energy intensive process that doesn't take place. So I mentioned here that 2 things we are doing. One is cross polarization and another is magic angle spinning, CP mass. CP stands for cross polarization, mass stands for magic angle spinning. But one problem with the mass, which I have told in the first class or the second class or in subsequent classes, is that mass averages dipole-dipole interaction. Since mass is something which averages dipole-dipole interaction. Why dipole-dipole interaction is getting averaged out? Because the dipole-dipole interaction is having an angular dependence or an angle term called 3 cos squared theta minus 1. This 3 cos squared theta minus 1 is an angular term which is a part of the dipolar Hamiltonian. I think it is not written it here, but it is there. In this case also it is there. A term is nothing but the first term, B term is also there. This 3 cos squared theta minus 1. Of course, in the other terms, it is not there. But these A and B terms, this is nothing but the dipolar Hamiltonian have 3 cos squared theta minus 1 dependence. So theta is equal to magic angle. At theta is equal to magic 54.74 degree, which is nothing but the magic angle. The 3 cos squared theta will become 1. 1 minus 1 becomes 0, and A and B become a very small value. That's a different aspect that we have discussed many times in the previous classes. So at the magic angle, what happened? A and B terms decreases. So if you do very high spinning speed, the high dipolar Hamiltonian reduces, or the extent of dipole-dipole interaction decreases, and this is not a favorable condition for a cross polarization experiment. Why? Because cross polarization experiment is the basis is nothing but the strong dipole-dipole interaction, which I have mentioned here. You see here, it is very important. The cross polarization occurs through the strong dipole-dipole interaction between proton and C13. If you try to destroy or if you try to play with the dipolar interaction, try to reduce its extent, the cross polarization extent also decreases. So one should have a what happened? One should have it's like a trade-off. One should have a trade-off. We should not spin at very high speed and we should not spin at very low speed also. If you spin at very high speed, we may get more resolution, but cross polarization will not take place. If you do at a very low speed, then what happens? Cross polarization will take place, but you will not get a resolution. So you should have a trade-off between magic angle spinning frequency as well as this dipole-dipole interaction, cross polarization. That is what I want to convey here. So that is why the narrow frequency range only this cross polarization takes place. That is what it is. Omega I, omega S. Now there is a narrow frequency range over which in omega this difference becomes 0. Then what happens? It will be a perfect. The difference between the frequency of proton in the rotating frame and the frequency of carbon that in the rotating frame becomes same. Then because omega I minus omega S becomes 0, then there is a maximum exchange or maximum cross polarization. And as the frequency changes, you can see the cross polarization extent is also decreases. So there is a narrow frequency range of gamma 1 and gamma 2 in which the cross polarization can be achieved. So it is not a particular frequency. There can be a width. in frequency in which the narrow range of frequency over which you can achieve the cross polarization. So that is why what happens in the cross polarization under magic angle spinning conditions. So that's a very, very important aspect. Under magic angle spinning, the heteronuclear dipolar coupling is average. So cross polarization in principle should not work because no more dipole-dipole interaction. But always, you know, you cannot go to very high spinning speed. You normally spin at a very normal frequencies like 10 kilohertz or 20 kilohertz. So under this condition, there can be a residual dipole-dipole interaction, and this residual dipole-dipole interaction can be employed for getting high resolution CP mass and NMR spectra. But that is what I am writing here. Coupling is not getting completely averaged out. So there is a residual coupling always existing. So under these conditions, under rotating conditions or under the magic angle spinning condition, the Hartmann-Hahn condition modifies like this. Gamma I is nothing but the gyromagnetic ratio of proton. B1 is I is nothing but the applied radio frequency for proton. And this is gamma S is nothing but the gyromagnetic ratio of carbon 13 B1 is plus or minus N. N can be 1, 2, 3, etc. At longer mixing times. So what is mixing time? Which probably I might have mixed something. Mixing time is nothing but the contact time. Contact time or locking time is nothing but the mixing time. Here I have indicated na mixing time. You see here, this is the mixing time. For some people say as the locking time, some people say as the contact time. So if the mixing time is more, then what happens? Then also the population transfer also will be effective. So when the speed is very, very high, so we increase the mixing time so that we get a proper polarization transfer from one nuclei to the other. That is what we are writing with the n is equal to 1 plus or minus 1, 2, etc. So here you see mixing time increases. Once the mixing time increases or the contact time increases from 1 millisecond to 60 millisecond, this intensity of the peak, this is nothing but the cross polarization peak, will keep on increasing. So this is what happening in magic angle spinning because the cross polarization get discrete. So discrete frequencies it happens, cross polarization. So that is represented by this type of expression. So in such cases, when you have high magic angle spinning, we slightly modify the pulse sequence, and instead of CP, we have a variable technique called VACP. VACP is nothing but variable amplitude cross polarization. We use different amplitude pulses. Previously, you know, it is like a straight line here. Now the straight line is not there. We have got a variety of pulse intensities. And this pulse modulated with the carrier frequency we apply. That is why we call a modulated pulse sequence apply or variable amplitude pulse sequence we apply, and the technique is called a variable amplitude cross polarization. So whenever we go for a very high resolution, a very high spinning speed NMR or very high resolution NMR, the cross polarization technique slightly changes and we will get VACP, or we will move towards something called variable amplitude cross polarization experiment. And as a result of this, you can see improved intensity. See, this is what the intensity we get from normal CP. The moment you go to VACP, you see the intensity improves. So these are from amino acid, typical amino acid signals. So you can significantly improve the signal by doing variable amplitude cross polarization. So far I discussed about cross polarization technique. Now I will discuss about some examples. So typical examples which you may encounter in your studies or in your research program, let us study that. A typical 2-3 examples let us discuss, and how the CP help in understanding the structure of the material. This compound, most of the people who are knowing, who are studied MSc, BSc must be definitely knowing. Organic chemistry must be knowing. This compound is called adamantane. Adamantane is an organic compound. So within few seconds, you can get an NMR in solution state. It's a very, very simple system. Only 2 types of protons are only there here. One is at this tertiary carbon, which is a CH proton. You see here CH proton. And we have got a CH2 proton. You see here CH2 proton. CH2 protons are there and C protons are there. Correct? Now CH protons are there. CH2 protons are there. Story is different in solution. Solution, you know, solution carbon 13 we used to do decouple and we get 2 signals only in NMR. Carbon 13 signal, we get only 2 carbon 13 signal. One corresponding to this methylene proton or the CH2 proton, and other corresponding to the CH proton. There are 4 CH proton and 6 CH2 protons. But in solid state, slightly different. Why? Because solid state, it is having a crystal system. It is having a tetragonal structure. Not only that, it is FCC at 300 Kelvin. This adamantine molecule is FCC or adamantine crystals are phase-centered cubic at 300 Kelvin, and it goes to the tetragonal form at 208 Kelvin. If you do solution NMR, you see how much sharp line you are getting. You see the solution NMR of adamantine. Adamantine gives two peaks. One is characteristic of the CH2 peak, which is nothing but this peak, CH2 peak. The CH2 peak is this one. This one number is nothing but this peak. And second, which is nothing but the CH carbon, is nothing but this peak. Of course, this is only two hydrogens are there, so we get improved intensity, whereas only one hydrogen is there, so we get less intensity. Because two hydrogens are there means what happens? Cross polarization extent is quite high, whereas one hydrogen is there means only cross polarization is less. So that is why you get a slight. This is a qualitative way of explaining. So you can say less intensity for this proton, this carbon, not proton. This is a carbon 13 NMR, and this signal is less intensity compared to this carbon number indicated as 1. Sorry, I just water. So very well one can see the two types of carbon 13 present in the molecule adamantine, one here, one here. Let us move further. This adamantine is having a property, it undergoes phase transition from cubic to tetragonal at low temperature. If you do, this is adamantine is used as a standard for testing, for setting the CP mass condition. Whenever you want to do a solid state NMR, if you want to do a CP mass NMR, we need to set the experiment for CP mass. Because as I mentioned, it's a double resonance experiment. The two nuclei, you have to tune in such a way, and you have to achieve the Hartmann hand condition. You have to change the magnetic field, you have to change the pulse width, etc. in such a way so that you get the frequencies in the rotating frame of carbon 13 and proton side. Then only this enhancement you can get. That is why setting a CP mass NMR experiment is tricky, and you have to do some experience to set this CP mass NMR experiment. Once you set that CP mass NMR experiment, we take adamantine as a standard, and using this standard, we record an NMR, and we get a solid state NMR of this type. So this is characteristic of the CH2 group, and this is CH2 group of adamantine. CH2 group of adamantine is nothing but this carbon. This carbon only two types of carbon, one carbon here and one carbon. Rest are same only. CH carbon and a CH2 carbon. And this peak is because of the CH2 carbon, and this peak is because of the CH carbon. Only single peak you can get, and you can also measure the line width. This should be around 2.5 or 3 hertz. If you are getting that, then we say we have achieved a perfect CP mass condition, and you can do a good CP mass NMR experiment. So that is the adamantine is used as a standard to check whether we can get the Hartmann hand condition, and we can go ahead with the CP mass NMR experiment. So this is the typical experiment we do for finding out whether the Hartmann hand condition is achieved, whether which is a proper CP mass NMR can be done or not. So again, I am just showing you the CP mass NMR of an organic compound called 2,2-bipyridine. So this is a bipyridine ligand. Once it is complex with the iron or it complex with the transition metal, because these type of complexes now undergo phase transition, means spin transition they undergo from low spin to high spin depending upon temperature. So this can have application in spin-based electronics, etc., because they have from high spin to low spin transition is possible as a function of temperature. So the interest of doing this type of work is if you confine these type of complexes in pores of CL8 or some metal organic frameworks or porous material, then its magnetic response changes. So keeping that in mind only, people have carried out this experiment, and this molecule, what happens to this pyridine ligand if you put the complex inside the pores or in the CL8 pores is given by the C13 mass NMR or the C13 CP mass NMR of this complex bipyridine or the bipyridine complex. So whatever the ligand, which is nothing but the bipyridine NMR is here, you have 1, 2, 3, 4, 5. 5 peaks are seen. Correct now? 5 peaks we are able to see. 1, 2, 3. It was to 5 peaks are seen actually. 1, 2, 3, 4, 5 peaks, 5 different carbon atoms are there. In fact, we can index these carbon atoms, C2, C3, C4, C5, 6 also we can integrate, the sixth carbon also we can integrate, total 5 only, but one number 1 is given to nitrogen. So since the number 1 is given to nitrogen, the 5 carbon, 5th carbon becomes 6th carbon. So that is why C1, C2, C3, you can assign these values. This is matching with the literature only, or the literature reports or solution NMR pattern. You can see here. 2,2- bipyridine is having a carbon atom. These are all benzenic carbon atoms or phenyl carbon atoms. So these phenyl carbon atoms are de-shielded like anything because sp2 hybridization is more shielded. So compared to sp3 is more symmetric, S character is less, P character is more, sp2 is having more this one carbon atom, but because of the ring current effect, we get a higher chemical shift value. In the case of sp3 carbon atom, even though the shielding is less, because there is no ring current effect, that is why we are getting a higher, we are not getting higher chemical shift value, lower chemical shift value, whereas these carbons are having a higher chemical shift value in the C30 because they are aromatic carbon or phenylic carbon. So that is why you see here C1, C2, C3, and the moment you form complex, the C3 and C5, C3 here and C5 here, they are giving a more or less same signal. The one thing you can see is the complex, the moment the complex get incorporated into the CL8, you see here, the many peaks disappear. So the complex get distorted. The complex is distorted, the peaks overlap each other, so the geometry changes. In fact, the transition temperature depends upon the geometry. So that is why the transition magnetic properties, if you study, the distortion in the magnetic field, distortion in the complex results also in the change in the magnetic field or the magnetic field created by the molecule. So this property has been studied, and the information obtained by through the distortion of the complex is useful for explaining the magnetic properties of these complexes. Another important material, many of you must be working on compound called graphene, graphite, etc. Because nowadays graphene is a very important material. People say that it has got a variety of properties. It can be used for photovoltaic application. It can be used for hydrogen storage, and all those things. Many people are working on that, supercapacitors, etc. And also used in IoT devices, etc. This is a potential material. A lot of work is going on, and we all know the graphene is nothing but the layered material. 2D materials are candidates for next generation electronic devices because silicon cannot go very high frequencies, 10 raised to 10 hertz. If you want to go for a terahertz spectroscopy or a very high frequency, then you have to go for a two-dimensional materials like a MOS2, graphene oxide, etc. because their frequency or the response times are quite faster. So how graphene oxide is prepared? In fact, graphene is prepared through the reduction of graphene oxide. So first they take graphene and a graphite, which is commonly available, and with the help of a method called Hammer's method, which uses acids, high concentration of acids, nitrates, etc., and generate something called graphene oxide. So graphene oxide is nothing but is a semiconductor, or you can say some sort of an insulator, whereas graphene is a metal. Graphite is also a metallic nature because its conductivity is very poor. It is conducting in nature. So the moment graphite is converted to graphite oxide and graphite oxide or graphene oxide is converted to graphene, then the electrical conductivity changes. So the conductivity can be monitored, and in fact the NMR response also changes. NMR normally does not give signal for conducting samples because the radio frequency cannot penetrate the conducting samples because of this electron skin depth. So radio frequency cannot penetrate. So we need to have either insulating samples or semiconducting for doing NMR experiment. So graphene oxide, now if you see, there are a lot of functional groups present on the graphene oxide prepared by the Hammer's method. One is the epoxide linkages. There is nothing but the OH groups which are coming on the surface, and the sp2 carbon is also there. sp2 carbon anyway will be there because graphite is nothing but sp2 carbon only. So this indicates that the graphene oxide prepared can be functionalized with the help of surface group present in this. And another important aspect is also there is an exchange of magnetization between epoxide and this sp2 carbon. And this has been proved by NMR spectroscopy. I will discuss with that slide right now. I will discuss because how you say there's an exchange of magnetization. If you do a two-dimensional NMR, if you do a correlation spectroscopy, if you do this probably next class I will discuss regarding the correlation spectroscopy. If there is a C13 correlation spectroscopy, if you do, then you can say there's a communication between the sp2 carbon as well as this epoxy carbon. This is a very, very important aspect. There's a magnetization exchange taking place between sp2 because there is why we are seeing a cross peaks. So diagonal peaks are their characteristic of these two peaks are here and this peak is here, but there is a communication occurring between these two peaks. That is why we see a magnetization exchange between the sp2 carbon and the CO epoxy carbon. This information is very, very important if you consider for the electronic application of the graphite, because now graphene is generated from graphite oxide by suitable conditions or suitable treatments. Now let us proceed further on adamantane itself. This I will discuss it when we discuss, since I have shown the one-dimensional NMR. So the relevance of the one-dimensional NMR or relevance of the doing an NMR experiment, CP-mass NMR I have shown. But we will come back to that in detail maybe towards the end of next class. Now let us continue further, maybe another few minutes I will say. One is a process called spin diffusion in adamantane. It's a very, very interesting phenomenon. If you have adamantane, what happens? Adamantane is a very peculiar nucleus. In solid state, as I told, it's room temperature, it's tetragonal system. Sorry, at room temperature, it's an FCC system, and it gets converted. I have mentioned here at 300 Kelvin at room temperature is FCC, and it gets modified to 280 Kelvin to a different crystallographic system called the tetragonal system. But adamantane is also having a very, very important property. See, as I mentioned, there are two types of carbon in adamantane. One is CH carbon and another is CH2 carbon. CH carbon is coming at a lower frequency. It is more shielded compared to CH2 carbon. This is CH2 carbon and this is CH carbon. If you see the chemical shift, this is more shielded. It is a smaller value compared to this value. Delta will be higher for this carbon and delta will be higher for this. Delta will be lower for the CH carbon. So normally what happens, this is a normal, there is no cross polarization here, normal single pulse, single resonance, no decoupling here, no CP mass here. If you do a C13 magic angle, simple C13 magic NMR spectra, if you see here, the peak which are seen here, as you increase the frequency of rotation, this is as a magic angle spinning increases, the line width increases. You see here, the line width increases. Why this line width is increasing? Normally one would expect, because once you keep on increasing the spinning frequency, the homogeneity increases. Once the homogeneity increases, the line width decreases. We should see a decrease in line width, but this is not happening. This is because there is an exchange of spins between the CH and CH3 protons. The protons of the carbon-13 can exchange between the protons of the CH2. The spin diffusion is a process by which the magnetization can be exchanged spontaneously between spins. The proton can exchange spin with carbon-13. I'm sorry, if I am mistaken that the protons, among the protons I exchange is not correct. Protons attached with the carbon-13 can exchange the spins with that of carbon-13. So there can be exchange of protons between carbon-13 and the proton, and as a result of this you get a broad peak. If there is no exchange, we should have seen a coupling. Correct now, we should have seen two peaks here, because here is a one proton is there. So this carbon should appear as a doublet because of carbon-13 proton coupling. But we are not seeing that, because there is a spin is getting exchanged between carbon-13 and hydrogen. So there is a spin exchange or spin diffusion between carbon-13 and hydrogen. We are not able to get a signal. There is an exchange process taking place, and we get a broad signal at this value. Similarly, here also exchange is taking place. Once the exchange becomes very fast, we will not be able to distinguish, and we should get a very sharp line. Once the exchange becomes very slow, if there is no exchange is there, we should get a doublet. But in between speed, you get a broad peak. That is what we see, a broad peak. Here, there's a sharp peak is also taking place, because there's a fast exchange is also taking place, and there's a slow exchange is also there. These two processes are mixed here. Slow exchange and fast exchange. Here there's a relatively slow exchange is taking place. The fast exchange leads to sharp line, whereas the slow exchange leads to slow line. The process is driven by the dipole-dipole coupling and is therefore related to the internuclear distance. So again, I will give, I think probably with this I stop here, but I think with this slide I will stop. The spin diffusion is a process in which magnetization can be exchanged spontaneously between spins. The process is dipole by, if there is no dipole coupling, then we will not see that actually. Because in solution we see coupling, but solution what we see coupling is not dipole coupling, it is a scalar coupling, it is taking place through the through bond or the through J coupling. That is why I have written JCH, which is around 131 Hz, and JCH, which is around 136 Hz. Through this coupling, we see the splitting. Whereas in solids, what we see is because of the dipole coupling. If you can do one thing, if you can replace part of the proton with the deuterium, then what happens? The proton-proton coupling decreases. So then you may be able to see a carbon-13 hydrogen coupling in solids also. So isotopic exchange also normally done to see whether it's a CH proton or a CH2 proton, etc. in amino acid to distinguish the type of carbon. So this just I told one example of spin diffusion, how they affect the light shape and how we can get information from that. The spin diffusion coefficient is smaller. If the spin diffusion is smaller, then splitting can be seen. If the spin diffusion coefficient is larger, then the broad peak is observed. Now this with this slide I stop. Normally in solid state NMR, we normally does not do proton. Why we do not do proton? Because proton gamma value is very high. Gamma value is very high, so dipole coupling constant is very high. As I mentioned, the dipolar Hamiltonian depends upon the gamma I value. So since proton there is a very high value of gamma I, the proton signal will be invariably large like this. So this is a particular organic compound they have shown it's a very large. But that is why people use low. If proton is attached with a low gamma nuclei like carbon-13, then it is advantageous. We can transfer that population to carbon-13 and we can get a beautiful signal for carbon. It's a beautiful experiment in which you take a nuclei which we cannot probe, but the population can be transferred to other nucleus and we can probe that nucleus. So that is what we see here. Carbon-13 can be very used to probe the NMR. But nowadays, pulse sequences and modern techniques are available, new techniques are available in which you can get rid of this dipole-dipole coupling and you can get resembling good signals from proton. Probably I may discuss at the last class, maybe at the 12th lecture regarding this. I think for the time being I will stop. Please feel free to stop me, and also you can also ask me any clarification or any questions or any problems. Kindly go through the assignments which have been uploaded in the website. Feel free to raise any questions. Very good, thank you.
Someone has written something, no?
Someone has, it is clear somebody has written. So this lecture I will mail you today. Shall I? Okay, the 8th lecture is over. Now the next lecture is on Monday. Monday is the 9th lecture. So that week I will be taking 3 lectures, and maybe next Monday 31st also I may take a lecture. So with that we will try to wind up. But you go through the whatever I have taught. Probably we can discuss something. I may have made some mistakes. You also, if you go through critically, then it will be a good thing. We can discuss thoroughly. Anything we can discuss regarding this. So please feel free to raise any questions. So today I am going to conclude with this. So thank you very much. Have a nice day. We will meet on Monday.
Thank you.